And indeed, we were just discussing something that is rotating around another point, okay, in a complete circle. We will be still keeping the shape of the circle intact. We are not discussing any ellipse or any other kind of motion like that. But now, in that motion, we are adding friction, okay? We are adding friction, and we are also talking about the centripetal force and centrifugal force. So these are few things which we are going to learn, which are a little bit new to you guys at this point. So I'm reviewing this slide from the chapter 4. You guys know that when we talked about the object that is rotating in a circle, and if the condition what we are still putting on, that the velocity is going to be the speed is going to be constant, right? The velocity, of course, is changing just because the direction of the velocity is changing, not the magnitude. The magnitude, which is the speed, it will remain the same. So that is being said, we also know that the acceleration for the uniform circular motion, the equation for that is v squared by r, and v in this case is representing the magnitude of the velocity, and r is the radius of the circle. This is something which we learned in chapter 4. Now, we also said that if an object complete one circle, like one revolution, it goes from one point in a circle completely to the same point back again, then we will be saying that it has completed one circle. And the distance it has covered, it is equal to the circumference, which is 2 pi r. And when we divide by the speed of the object, then what we get is time period. So what is time period? Time period is the time needed for the particle to complete one circle. And r one revolution, you can say it. Okay, so if it can complete one revolution in the time, that time will be called time period. So these two formulas, a equal to v squared by r, or t equal to 2 pi r divided by v, these are the two formulas introduced in chapter 4. And from now on, we will be beginning to bring a little bit new dimensions to it. But here I'm calling this acceleration, which you are seeing v squared by r. It's not just acceleration. From now on, I will be calling it centripetal acceleration. Centripetal. Centripetal means towards the center. So always, if you look at this circle, right, on the right side, you are seeing this circle here. And no matter where you are, when you look at the direction of the circle, the acceleration, it will be always pointed to the center of the circle. It is either here or anywhere else in the circle. It will be always pointed to the circle. Whenever we are talking about the velocity at any point, the velocity is just tangent to the circle. Okay, like here, if you want to talk about the velocity, it will be tangent here, tangent here, tangent here. No matter where you want to talk about the velocity, it will. So these things we know it. Now, here in this diagram, what you see is that there is a guy and he's having a heavy ball, and that ball he's kind of attached with a string, and he's holding it from the string and rotating. So he's rotating around himself. Okay, so this part of the ball is called orbit, or just you can say circle, right? It is a circle, and since the length of his arm and this string, both of them, we are considering it fixed. Okay, the string is not like a rubber, it's more like a metal rod, you can consider it. So it doesn't move. Okay, so whenever he is rotating it about its point, this is the axis of his body. Around this axis, he is rotating this ball in a complete circle. At any point along the line, whenever we want to discuss the velocity, it will be always a tangent. If you are considering here, it will be velocity here. If you are considering this point, it will be here, like the same as you are seeing in the previous diagram. And one thing more which I want to bring in is the centripetal force, because we mentioned that the acceleration of v squared by r here, this is the centripetal acceleration. Now, whenever there is acceleration and we multiply that with the mass, then that becomes a force, because by Newton's second law, F equal to ma. And since the A is V squared by R, so mv squared by R is giving me a force. And the name of that force is centripetal force. What is centripetal force? It is the force which keeps the body to move in the circle. And there is another, when we, by Newton's third law, we know that there is an action, which is the centripetal force. There is a reaction, because when you are rotating the ball is always trying to go away from you. This tendency of the ball to go away from you is coming from a force, and that is called centrifugal force. Centrifugal force is meaning that the force that is moving things away from the circle. Centripetal force is the force which is bringing things towards the center. So these are the forces, okay? So the force shape, like the formula, whenever we are talking about, it will be always mv squared by r. And this v squared by r is coming from the centripetal acceleration. Well, there are different kinds of centripetal forces, and also the shape of them are changing. But nonetheless, no matter what shape of the centripetal force we talk about, which type of the force we talk about at the end, the formula is going to be m equal to v squared by r. And here is an example. For example, you see there is a satellite, and that satellite is orbiting around the Earth. What is the force between the satellite and the Earth? Can someone tell me that?
Gravitational force.
Gravitational force. So between the satellite and the Earth, that's a gravitational force. It is not a string attached between the two things. It is not physical objects, but rather than it is a force. You cannot see it, but it is there, right? And you can experience it. So that is the centripetal force, which is the gravitational force. Whenever we talk about the gravitational force, we know, first of all, that Fg is the mass times acceleration. And the acceleration is again coming from mv squared by r. So the shape of the force is mv squared by r, exactly like in the previous case. Now, another thing is the car going in a circular path around the on a road. So, for example, you are driving your car. Sometimes you are taking turns, and the turns could be considered as a part of a circle. It's not a complete circle, but part of a circle, right? And in that case, what is holding your car on the road? You are still, like, you are in the high speed, but still your car is not sliding away from the circle. Like whatever the road is, you are still sticking into that, and you are moving. So if you look at that, the centripetal force in that case is the friction force. And the friction force comes between the tires, which is the rubber, and the road. So between the rubber, the tire, and the road, there is a friction. And that friction is the static friction. Again, here we are talking about the force, centripetal force. Now the type of the force is different. In the first case, it was gravitational. In this case, it is the frictional force. Again, it begins from Newton's second law, F equal to ma, but the final shape of the force is mv squared by r. I can determine this frictional force just by using this equation, which is the mv squared by r. Now, in the third case, exactly like the case we observed in the previous diagram, there is a guy again holding this ball, and he's rotating around himself. So he's moving the ball in the circle, okay? Now, in this case, the connection between the ball and the person is via this string, since the string is attached and the guy is holding the string. So the centripetal force in this case is the tension force, because the tension force we always talk about, if you are transferring your force via a medium, like a physical medium, like a string or wire or something like that, then there is a tension in that. And that tension here, it is certainly pointing away from the ball towards the person. And that is T equal to, again, ma. And since this is the A is coming from the centripetal acceleration, so it will be mv squared by r at the end. All these three things, all these three cases, gravitational force, frictional force, and tension forces, these are three different types of forces, but in all cases, the end formula for the centripetal force is the same. mass times v squared by r. And the v squared by r, we know it is the centripetal acceleration. Okay.
Doctor,
Do you have any
question
here? Yeah.
Yes, I have question.
Yeah.
In the first case, does the acceleration of gravity equal to v squared over r? So
yes.
9.8 equal to this?
That is, you should be careful in that. Here we are using the word acceleration. We are not using the word gravitational acceleration, which is 9.8 meter per second square. Because whenever you are going into that high level, the value of the gravitational acceleration drops significantly. It is no longer 9.8. As you are
so
going
it's not
up,
a constant.
It's no longer constant.
Oh, okay.
Whenever we are using the term g, which is the gravitational acceleration, if you notice, most of the cases we will be just talking about the top of the building or the 100 meters away from the surface of the earth and something like that. But we just don't talk about so much high that where there is no gravitational acceleration, or the gravitational acceleration is significantly low. So g, which is the value of which has the value of 9.8 meter per second square, later on we will be deriving that value changes as you are going away from the earth. So up to the few kilometers from the surface of the earth, it is approximately 9.8. But if you go significantly high, like to the level of the orbiting a satellite, so then in those orbits, g is significantly low.
And in the second case, why the friction is static? Because the body is moving.
Yeah, the body is moving. This is a very good question, and I will be clarifying it multiple times in future. That you know that the car is going in the forward direction. That's one thing, right? And whenever the car is going in this direction, but if you look at the friction is in the opposite direction, right? So if the car was sliding, like let's say you put some lubricants and the car was skidding outside, then in that case it will be kinetic friction. But your car is going at any point at which the tire is touching the road, it is static. And if it was skidding, means that the car was going away from the circle, then that will be the kinetic friction. You got the point?
So do you mean that the car, according to the center of the circle, it's static?
It is static, but let's say this is the circle. Okay, this is your roundabout, and you are going in the roundabout like this. If you look at that, your car goes in a circle like this. Okay, so at any point, even though your wheel are rolling, but at any point when the wheel is touching the road, it is static with respect to the center of the circle. Okay, if your car was skidding, like your car is moving away from the circle like this, there is some slip, then in that case the friction force will be kinetic friction. Okay. Any other point? These are good questions. Yeah.
Yeah, teacher. If the first concept, force of gravity.
Okay.
What happens if like the spaceship is not moving? If it's not moving, then there is no force.
The spaceships are always moving, and I will tell you that the spaceship is always, even though we are seeing it at geocentric or kind of a static or stationary satellites, but in reality they are keep moving. Like if you fix them on top of New York, it will be staying on top of New York. So since the Earth is rotating, along with that, this is also rotating. So there is a fair amount of speed for that.
Huh.
Yeah. Any other question?
Wait, how is that happening? Wait, the satellite is actually moving with the Earth?
Since the Earth itself is rotating, right? You are rotating like the ball. If you consider the ball itself is rotating. But if you are away from the ball, then you have to have much more speed in order to keep the same point like that, right? Because the speed is 2.r divided by t, and since for the small circle and the bigger circle, the time is the same. but the 2 pi r, the radius is making a big difference. So the satellite is away, therefore its speed is significantly high. Yeah.
Okay.
Yeah.
Doctor,
Yes.
these do not represent the net force, right?
T, you mean?
All of them.
They
Do
are
they
not
mean-
representing the net. Yeah, this is a mv squared by r here. This is in a way is a net force because you by Newton's second law, we know that the F net is equal to ma. Since whatever the force we have here, like the friction in this case, that is the net force, because for the car, like there is air, but we have neglected the effect of the air. For the satellite, there are other kinds of forces from other objects, and we are neglecting them because they are so small. Yeah.
So the gravity does not affect on it?
The gravity has, you mean in the first case, the orbit?
Or I mean the guy with the...
Yeah, the
With the
guy, when you are looking at the guy, that diagram is a little bit misleading, and I wish that if I could find a better picture, because the way in which you are seeing it, it is moving up and down, right? So since he's moving this up and down, so there is another force acting, but that force is vertical, like along the y-axis. Okay, but if he's moving like that, then we have to resolve the tension force in two components, and therefore that is the thing, which is kind of making it complicated. For now, what I would try to explain it in this way, that consider that the guy is moving the ball in the same plane, not moving up and down, just moving in the same plane. So yeah, you have a good observation there, but ignore that effect. Yeah.
Okay.
Yeah. Okay. So there is this checkpoint about this rotational motion. You might have been went to some amusement parks, and there is a Ferris wheel. The Ferris wheel is that the kind of amusement park, like kind of a big wheel. You sit on there, and then the wheel is taking you up and down. Since the seat position when you sit on this, it is taking you like that, like as you are seeing in the diagram. Your position always stay up. Either you are in the top of the wheel or at bottom of the wheel, but your seat position stays like that. It is always vertically up. Your head is towards the sky. So when you ride a Ferris wheel at constant speed, what are the directions of your acceleration A and the normal force Fn on you from the always upright seat as you pass through the highest point and the lowest point of the ride? So can someone tell what will be the situation, like if you are passing the highest point, how many forces are acting here? Like in this location.
3.
How many forces are there?
3.
What kind of forces are there?
Gravity.
One is the Fn, someone said it. Okay.
Yeah.
Fn is upward.
FG.
And which force?
Weight.
And
Weight is downward because the guy is sitting on the seat, so the weight is downward, mg is downward.
And the
And the
central
centripetal
refugio
force.
force.
And then there is centripetal force because this object is still rotating in the circle. So there are three forces for that while it is in the upright position up there. What will be different at the bottom, which is shown at the lower side here, like this one, this diagram. Since the Fn is up still, and the gravitational force is still down, but the force, which is the centripetal force, it will be up because the guy is, we are talking about this position. So he's still keeping the motion in the circle. And we know that the centripetal acceleration always will be pointing towards the center. Okay. Checkpoint, again, it's the continuation of the checkpoint. How do the magnitude of the normal force compare to at those 2 points? How we can compare the normal force at those 2 points now? Can you formulate this force here?
The left side, the normal force will be bigger than the
In
weight.
At
Yes.
the
the
top,
left
it will
side,
be
you
larger
can say that
than the
it's,
bottom.
Okay, so that's one of your opinion, right? Because here you are saying that if this will be Fn, this is one force minus mg, this is another force, and then we are getting minus mv square, right, by r. And the negative signs are coming just because we are keeping the convention towards negative y-axis negative. So this force, the Fn, at the top is going to be smaller, okay? Because when you move the mg to the right side, this term will be subtracted from that. So it will be smaller at the top because you will see that when the guy go upward, he will be a little bit feeling a little bit moving away from the center, right? Like there is a kind of a little bit fair amount of jump there based on the speed. Okay, so when you look at the bottom position, you again keep the same formula set, but now instead of negative sign for this one, it will be positive. And then you get at the end this formula, because you may have noticed that when you are passing through the bottom, you are pushing the seat a little more harder. And more harder means that as a reaction, the seat will also have upward force accordingly more. The last point is, how does the magnitude of the acceleration at the highest point compare with it at the lowest point? So since we know this equation now, this is one of our equation and this is second equation, all you need to do is to solve this for the v squared by r, and that will give you the answer for the last one, which is already shown there. Okay, let me do this problem, guys.
Doctor, I don't understand.
Yes.
The point just now.
Yeah.
I don't see how mg minus, if you could go back. I don't see how mg minus v squared over r. I don't understand this. Yeah.
You mean this point? This point? You didn't understand this one?
No.
Which point you did not understand?
Yeah, I can't imagine how is that the case. Isn't Fn going to be equal to the forces down?
Yeah. So there is something which we need to know. There are two forces on this object. Let me draw it here on the diagram. When you are at the top of the wheel, like this position here, right? This location. Since you are sitting on this seat on top, so the seat is pushing you upward, right? It is providing you support upward, and your weight is pushing you downward. So that is the weight. These two are the forces. This is all you have now. If you are at rest, like the wheel is not rotating, then these are the two forces you have. It doesn't matter whether you are up, you are down, or you are at the sides. All the times, this is what you have. But now, the wheel is rotating. The wheel is rotating, and the wheel is always trying to bring you towards the center. Means that it is keeping you in the circle. If you are not tied to the seat, and the wheel goes faster, what will happen to you? You will be tossed out, right?
Yeah.
You will be tossed out. So since you are strained, you are tied to the seat, and the seat is trying, like the entire wheel is trying to rotate you around itself. So therefore, just because of the motion of the wheel, there is acceleration, and that acceleration is downward. Okay, so by Newton's second law, when we are applying this, we say F net is equal to ma. So in this case, when I'm distributing the forces, I put the x and y axis. So plus y and minus y. I consider Fn positive minus mg. These are the two forces. And under the action of these two forces, you are rotated. So there is the net force which is coming from the A, right? And since the shape of the A for the circular motion is v squared by r. V squared by R. So that's what you have it.
Oh yeah, so yeah, I get this.
Okay. What is that? Please raise your voice. Okay, I don't hear you.
I don't know.
I think he
I
doesn't.
get it now. Yeah. But for some reason, when I look at the next slide,
This one?
it seems like there's minus.
Where is minus?
mg minus v squared over r.
This is the I choose the minus sign for this one because I should be consistent here because this acceleration is pointing to the negative side. Fn is pointing to the positive side. I took it positive. Mg, it is pointing to the negative side. I took it negative. Okay. Since this acceleration is also pointing to the negative side, therefore there is this negative sign here. Yes, there is negative sign. But when you are going in the opposite direction, when your seat is here, then the normal force is upward, and then the v squared by r is upward, and the m is downward. So accordingly, just because of the convention, you also have that. But the only thing that will be different is that the sign of the v squared by r.
mg and ma, they're in the same direction, shouldn't they? Like have the same sign?
No, they are not in the same. What do you mean? This one, right?
Yeah.
Yeah. So this is why it has the minus mg, and here you have minus v squared by r. You can put this negative sign here if you want.
Yeah, but like if I put the mg in the other side, they have different signs. I'm wondering.
You should not be putting like that. Okay, let me explain it. I think I got your confusion. Why you are confused here? Let's say you have two friends, and one is pushing the car from the back side, and another one is pushing the car from the front side. The car was initially at rest, and two friends are applying the same amount of force. Will you be able to move the car?
No.
No, because the acceleration is 0. You are saying friend number 1 minus friend number 2 is equal to 0.
Yeah.
But if you were able to move the car, like you are friend number 1, and you were able to move the car, what will be the sign of the acceleration?
Maybe positive, maybe negative.
Will be positive because your force is already considered in the positive direction. So it will be F minus F2 equal to plus MA. The car will move in the forward direction. And if the friend number 2 was stronger than friend number 1, then what will happen? That F1 minus F2 is going to yield negative MA because the car will be going in the opposite direction, in the reverse.
Yeah, so the MA here is the actual acceleration of this.
Because
so
this
that's
is
why.
MA. MA is the result of the forces. This is just because of the result we are seeing it. It is not itself a force. It is produced after applying the forces.
Yeah. Okay. Thank you.
Let's move on to this question here. Here in this figure, it shows an object of mass 0.1 kilogram tied to a rope, rotating in a horizontal circle of radius 0.25 meter on a frictionless tabletop. It rotates at constant speed of 4 meters per second. While the mass m is stationary, find the value of the mass m. So, okay. Here you are seeing this, the mass which is rotating on top of the circle, it has the tension downward because the tension is holding it from the center, right? So the tension is downward. And here you have, as a result, the tension force mv squared by r because there is a centripetal force just because of that. So mv squared by r is the tension just because of for the mass which is on top. Therefore, I'm taking it the small m. Then there is another mass which is hanging below the table, and the string is coming to that mass like this. That is capital mass. We know the tension with respect to that is upward. And they are saying this mass is stationary. It doesn't go up and down. So from that we assume that the T is equal to capital Mg. Just because the mass doesn't go up and down. If it was going up and down, we will be considering the effect of the motion. And then by the formula which I have been deriving, like positive minus negative force equal to 0 acceleration, and therefore we get T equal to mg. So here you have this equation 1 and equation 2, and we know that the tension right here in this string and tension right here in this string, both of these tensions are the same. So I will compare this equation with this equation, okay? And I will get it as capital Mg is equal to small m v squared by r. And then divide both sides by g just to get the mass. Okay, I got g here. So now I'm looking at the problem and looking at how many variables do I have. I have 0.1 kilogram, and then I have the velocity square, and that velocity square is 4 meter per second square. And then here I have 9.8 times the radius, and the radius is 0.25. 0.25. Everything is known, so I can determine the mass. Any question here?
Clear.
Okay. Guys, don't forget that there is a test which will begin at 12:40. So that will be on the blackboard. So remind me if I was still not paying attention to it.
Sir,
Okay.
I have a question.
Yes.
The midterm will be covering up until how much?
We can discuss that later, guys. Okay. Let's start. Yes. So sample problem. There is this daredevil. A daredevil is performing a skirt here. So he is coming on a bicycle, and when he is coming up with some speed, he is trying to rotate the circle loop, and then will be able to go out of it. So assuming that the loop is a circle with radius 2.7 meter, what is the least speed v that a daredevil and his bicycle could have at the top of the loop to remain in contact with there? Okay. So let me draw this diagram and pay attention to here. Let me know if you don't understand this point. He is coming in with bicycle and he is still going upside down. So there is this bicycle, okay, and there is the person, okay. Both of them, since they are below the surface, not above the surface, below the surface, so they are pushing the surface upward. So we know the normal force, the reaction force from the surface will be downward, which is Fn. Okay. We also know that the weight of the guy and the bicycle, both of them should be down, which is mg. Okay. Now, these things are known. Since this is going in a circle, and the circle there is a centripetal force that will be also towards the center, which is mv squared by r. Okay. So now we are putting the y-axis plus y minus y and considering all forces to the negative side negative. So Fn is negative, mg is negative, and as a result, we also get this negative. Okay, negative sign is everywhere, so we can multiply this with -1, it will become positive. But there is one more assumption. They are saying what is the minimum speed? What is the minimum speed that they can keep the bike just in contact? So by the minimum speed, what they actually mean that when the guy reaches to the surface of the circle, the upper part, he should be barely touching the surface. He is not applying any force on the circle. And if that was the case, then the surface will also have zero force applied on the person as a result. So in that minimum condition, this Fn is zero. Then I'm putting is mg is equal to mv square by r. The mass cancels out. It doesn't matter whether it is a bicycle or a truck or whatever. But if this is the circle size, it depends on the speed. So we can solve this. For the speed, we multiply both sides with r and take the square root. So v is equal to gr under the square root. This is all I got. V equal to g, which is 9.8, and the radius of the circle, which is 2.7. Both of them are given. We can determine the minimum speed for the guy. Any question here?
Yes, teacher.
Yes.
I didn't get how Fn is downward.
How Fn is downward, we know that the Fn is coming from the reaction, right? If you are sitting on top of the chair, you are giving trouble to the chair is giving you trouble, and that trouble is upward, right? So you are applying the weight, which is the force downward, as a reaction. There is another force, which is the normal force, that is upward, right? Okay, but if you are pushing something from the behind like this, okay, if you are reaching something from the behind, you are pushing that surface upward. As a reaction, the reaction force from the surface will be downward. You got this point?
Yes, I get it. Thank you so much.
Yeah, no problem. Any other question?
Doctor, if he, the normal force was zero, he will fall down.
The normal force is zero just because he's barely touching it. He is at the verge of leaving the surface. Like, you know that if you throw something upward and he's barely touching it, it's out of the energy right at the surface, then what will happen that he will be just detaching itself and will be coming down. This is the verge of leaving the surface, but not left yet. We are discussing the situation right there. Any other?
Quiz, Doctor, the quiz on the blackboard?
Yes, the quiz is on the blackboard. It is, what is the time? We still have a couple of minutes. Any other question? Okay. So there are a couple of more examples that I will try to spend some time on that, because I feel that they are very good examples. So I will discuss that in the next class. You guys just go now and log into your Blackboard account and stay there at 12:40. Your quiz will pop up and begin doing your quiz.
We will round our answer into scientific figures.
You will round the answer to the same decimal places as given in the problem.
Okay, thank you.
Yeah. And also, I noticed that last time the student, a couple of students, they had entered their answer in ratios. Don't enter your answer in ratios like a 2 divided by 3. No, the Blackboard doesn't recognize it. So I need to go and check them then manually. 2 by 3, do the calculation, whatever the answer you get, just put that number. Don't put 2 divided by 3.
Doctor, where is the quiz?
It's on the Blackboard at 12:40. Go log into your Blackboard accounts.
Okay, yeah, but where in the Blackboard?
Where on the Blackboard?
Assignments.
Assignments. Yeah.
Thank you.
Okay, it's 12:40. Refresh your window. It will appear there. It looks like you guys are texting each other so much. During the quiz, just focus on your quiz rather than sharing the information with each other. It's not justice to good students.
Teacher, I was texting. I can prove to you that it wasn't the group if you want to check.
I don't want to check. Just I trust you guys. You're old enough now.
Yeah, Doctor.
Yeah.
The radius of the Earth. Why does it matter? Because when we measure the gravity, we usually measure it to the surface, not to the inner core.
I don't want to discuss that, but the information are given to you in that. Yes, it's up to you however you want to solve the problem.
Can I ask you after we finish the exam?
Exactly. Yes. Yeah. Yeah, Rakan, you can go back and forth between questions, yes. Okay. Let me see. Which problem did you solve? Can you tell me? Which problem did you solve and which one you need to solve? I cannot read what you sent. Just tell me.
I said I didn't solve the first one. I skipped to the second, and I was going to go back, but it wouldn't let me.
The second problem was about what?
The second problem is a particle moves in the XY plane.
Okay. Okay.
Teacher.
Rakan, I sent you the question in the comments. Answer this question and send back the answer in this same comments box to me, not in the public. Yeah. Yes. What's the question?
For the final speed of the pen, do you want it in horizontal or vertical?
For the final speed of what?
Of the pen.
Of the pen?
Yeah. I'm not sure if I'm supposed to be asking this or not.
So it is the speed, right? It contains 2. Right? It is some like magnitude of the velocity. That's the hint I can give you.
Doctor, can you please check if you received my answers?
Rakan?
Abdurrahman Jayed.
At the end, just
okay.
Doctor, yes, I finished my quiz. Can I ask you now or after the class time?
Like once the quiz time is over, then I can share all information.
Should I send an email to you or wait until you end?
Yes, you can send anytime. Yeah.
Sir, I finished my exam. Can I leave?
Yes, if you're done with the exam, yes.
Thank you. See you tomorrow.
See you.
Thank you very much. See you tomorrow.
What is that? What is your question?
My question?
You said something, yeah.
No, someone said thank you. That's it.
Oh, okay. You're welcome.
Doctor, want to discuss the thing with the acceleration direction. Is it fine if I ask you now?
The class, yeah, the quiz time is over. Yeah, ask what is the
so when we want to know the force going down, the centripetal force, like shouldn't we use something other than the resultant, because the resultant would be both the force going to the center and the forces going to the ground. So wouldn't these two, shouldn't we differentiate between?
Rakan, what I sent you, just answer that question now, because this is a pool of questions. So just send this is considered, this is your unanswered question. Answer this one and send me the answer for this. One you already submitted to the blackboard, I will see one there. And the second one is this one, okay?
Doctor, can I leave? I finished the quiz.
Yes, you guys, if you finish the quiz, you can leave. Yes, guys.
Doctor.
Yeah.
Your slide need password to highlight or do something?
Yeah, because it is not allowed for edits. You cannot edit them, but you can read them.
But if I want to highlight sentence, I can't.
Because edits are not allowed, because it's creating a lot of trouble for me. Students, they play with the slides, and later on they claim that I did something wrong in the slides, and that's giving me more trouble then. Yeah.
Okay. And the grade for the quiz.
It should be shown in about 10 minutes or so, once the Blackboard compiles everything, and I will go over the grades as well.
Okay, thank you.
Yeah, yeah.
Is that okay?
What is that?
I got late.
When did you got late?
Yeah, me too, teacher.
When did you got late?
1 minute after.
1 minute
I
after
just
what?
got late at 12:51.
At 12:50, I
20:50.
get me at 12:50, and I get late.
Yeah.
12:50
You mean you got late message from the Blackboard, right?
Yeah.
Yes.
Don't worry about the late. Whatever
Yes.
you have submitted in the first 10 minutes, it will be accepted. Whatever you entered after the 10 minutes, the Blackboard will toss that out. It will not be accepted. But if you had entered before and you just got the late message, don't worry about the late message.
Thank you.
I sent my answers 10 seconds before the finish of time, and I got late. So is there any problem?
No problem. If you have submitted before your end time, everything is fine. The late message you get just because the due time and the end time, both of them are set at the same time, and that's why you guys are getting the late.
Doctor,
so the late message itself is not a problem. Yeah.
The grade after the submission is the final grade, or
once you submit that, I'm also going over all the grades, and I will check them if everything is fine.
So it's not the final grade, right?
If there was some problems in there, then I will fix them, and you will see your final grades afterward. And if there was no problem, your answers were whatever they are, then whatever you are seeing that could be considered as a final now.
Oh, okay.
Yeah. So there was a guy who was asking about the centripetal force, and I completely lost that question. Yeah.
It's okay, doctor.
Yeah. What is the question?
Yeah, about the force going to the middle of the ferry, let's say.
Yeah, the Ferris wheel, there is this Ferris wheel. It is different kinds of positions, okay? There will be the problems in which they will be saying that there is a seat, and in the seat the person is sitting upward like this. So your seat is pushing you upward and your weight is pushing you downward. So there is this mg is downward and the normal force is upward. These are the two forces which even though the wheel is at rest, you will have these two forces all the time. But if the wheel was moving, and since you are fastened to the seat by the seat belts and things, so the wheel is trying to move you with itself. It is applying some force on you, and that force is coming as an offset of between the two forces, and that is at the top. Since the wheel is rotating you towards the center, then therefore that is going to be towards the center as well. So this is the centripetal force. Since centripetal force is coming from the net force, like the net by the Newton's second law, ma. So the net force is generated by the Fn, which is positive, and minus mg, which is negative, and then this is minus mv squared by r. Yeah. So
yeah, this works. Yeah. I get this one. This works here.
Yeah.
But let's say if it was maybe a bit more down, not at the top.
You mean here?
A little bit above, in the middle. Yeah. Something like this. I think this
was
would.
Here,
yeah.
If it was here, then you will have a little bit difficult situation, and the situation that's at this point we don't bring into discussion, just because the students are not familiar with the total ideas. Once we build up the ideas at the easiest points, then we can challenge the students right here.
Yeah, for this one, the Fn and the Mg will be equal, so it doesn't.
No, it's not equal.
No, I mean the other one.
Yeah.
The one at the top. Sorry.
Then also
Fn.
Fn and Mg are not equal, because if they were equal, you will get 0. But they are not equal. That's why you are getting mv squared by r. Right here, when you are looking at the Fn and the Mg, Fn is upward, Mg is downward all the time in the entire circle. But what is now different? The difference is that here is the center of the wheel. There is the centripetal force. So the acceleration direction is this now, which is mv squared by r. Now you need to resolve this force in two components. One will be this component, another one is this component. Okay? So one downward, it will be the, if this was some angle that is subtending, then this will be the mv squared by r, and then this is the cosine theta, and the lower one is the mv squared by r sine theta. So then afterward, there are a little more complications coming into the to the forces, and then we have to resolve them in components and then decide based on that. Yeah.
Victor.
Yes.
About the question about the R.
Okay.
Is it now okay to ask?
Yes, yeah.
Since when do we measure the gravity to the core and not to the surface?
Always. Always.
But you always say, when we ask about the gravity and how much, you always said we measure the distance between the object and the surface.
The case is in the cases that when we are talking about the point particles like this, point particles we are representing it by some dot just because we cannot represent point, just exact point. Okay, so the point is just a single dust or even smaller, or the atom or the electron or even smaller, because it doesn't contain any dimensions. So by the point particles, you just extend the lines from one point to another point. But if there was this Earth, like this Earth, and there is this object satellite, when you are taking the distance, this is like this distance, because this is the distance between the two objects. Whenever we are talking about the distance between the two objects, we don't mean from the surface to this surface. Between the two objects, from the one center of the object to the next center of the second object. Rakan, your question is so late.
Okay, thank you.
Yeah. This is not the. It should be done within the reasonable amount of time when you submit this. Like if one minute was disturbed between you communicated with me and I sent you the question, I will be expecting that 1 minute extra to your quiz time. Like instead of 50, you can submit up to 12:51 or 12:52, but not 12:58. Yeah. Yes. Any other question? Munir? No, Munir is not there. Let me see if there is another. Yes. Okay. Musab, Yahya, you have any question? Or Hamad?
Oh yeah, doctor. Now I know how to say it a bit better.
Okay.
Let's say if it was on the right, like where the center force is going to the middle.
This one, right?
Yeah.
Uh-huh. Yeah.
The Fn and the Mg would be equal to each other.
Exactly.
Like the thing that I want to do is I want to say that there is a difference between like the force in the middle, the force that goes to the middle, and the actual force.
Exactly. Yes, because the centripetal force is not depending on these two forces. It is just telling you there are some forces, and this is the offset of the two forces. Okay, one and along that direction. And also the main confusion point is coming in most of the time students think that if it was written as Fn, it means a fixed force. But Fn is an extremely troublesome force. It keeps changing from point to point. So here it might be 1 Newton, but here it could be 10 Newton. You never know. You need to analyze the situation and then act based on it. So right here, yes, it is centripetal force is like this, and right there the seat is upward, which is downward force, and the mg is downward. So right here the Fn is complete to mg.
Yeah, so this is only centripetal force, but when we go a little bit up, it becomes 2 forces together.
Yeah, because this centripetal force now has an angle, and based on the angle, we have to resolve them along the x and y.
And the Fn has an angle too, right?
Fn has no angle because Fn, it is always along the y-axis, is in this situation.
In the ferry, yeah.
On y-axis, this is always along negative y-axis, so it just keep rotating like that. The angle comes from the centripetal force.
Yeah, so if the F of n is if it was with the velocity, so if it was going to right a bit, this wouldn't be correct.
Yeah.
Yeah, this was what was confusing me, because I used to solve questions like this, but without the F of n going up. I think this was it.
Yeah, this is one of the trick, and sometimes there will be sometime when they are bringing a little complication into the problem, they will be saying that the seat is upside down. Like the seat is fixed, but if the person is here, the person will be up like this, and if it is here, the person will be down like that. So then you also know that the direction of the Fn is completely different, and from point to point, it also keeps changing. So which is kind of bringing a lot of complication.
Yeah, this is the bicycle one. Okay, thank you very much, Doctor. Thank you very much.
Yeah. Ahmad?
Yeah.
Okay, that was okay. I'm sorry. Yeah.
The only thing that was confusing me, I swear, this is easy, Doctor. The only thing that was confusing me was the F of n. I always considered it like going right. I don't know.
That's what it is usually.
Yeah.
Okay.
I got 10 on the quiz, by the way. Yeah.
You got 10?
Yeah,
okay.
I have my proof.
Yeah.
Thank you, Doctor.
No problem.